Hi. My name is Takumi Kobayashi. I'm from National Institute of East in Japan. In this talk, I present my work about knowledge distillation. Generally speaking, higher capacity models are well trained to produce good performance, though the parameter size and computation is costly. On the other hand, the lower capacity models are light-weighted but perform poorly. The knowledge distillation is a technique to bridge the performance gap between low-capacity and high-capacity models. To that end, during training low-capacity student model, the method injects not only the supervised annotation information, such as labels, but also knowledge that the high-capacity teacher model has. Such a KD process is formulated in this loss function, which combines standard classification loss and cross-entropy between the softmax probabilities of student and teacher. Here, the key component is the temperature which is applied to these probabilities as well as the weight. This entanglement makes it hard to analyze KD. In this work, we analyze KD process by using a general formulation which disentangles three components. Based on the analysis, we propose extractive knowledge distillation. As in a chemical process of extractive distillation, we add the criterion of uniformity to further extract effective teacher's knowledge for improving performance of student. We introduce a general KD formulation to disentangle three key factors. The point is, two temperatures tau and tau s are introduced for teacher and student probabilities, respectively. Thereby, we can these three factors individually and analyze them as follows. The first analysis is about student probability. We measure performance by varying student and teacher temperatures. And, we can see that the student temperature produces small performance fluctuation, while the teacher temperature brings large performance variation. Student temperature is less contributive to performance and so, it is simply set to 1. Second, we analyze teacher probability. This is a key contribution in this work. As shown in the first analysis, higher temperature is required for teacher probability. It results in blurred probability. Such a blurred teacher knowledge has two effects. One is enhancement of class relationships. By blurring, the classes which are close to the ground truth one also become distinctive. This knowledge teaches favorable structure of feature space. The other effect is uniformity. The remaining irrelevant classes exhibit rather uniform probability by blurring. And, the uniformity works as regularization, as is the case with label smoothing technique. It improves generalization performance of student model. But, these two effects are entangled via teacher temperature. So, it is hard to properly control these two by using single parameter tau. We propose extractive distillation. First, it decomposes teacher probability into two parts of class relationships and uniformity, by thresholding the probability based on uniform probability. Then, they are remixed by a new parameter epsilon to finally produce teacher supervision. By doing this, we can flexibly control these two effects in KD. In the extractive distillation, we can improve performance by tuning two parameters, of temperature tau, and mixing rate epsilon. Such a parameter setting is robustly applicable to various datasets. The third analysis is about weighting. The weight should be large enough to properly balance the two gradients which are from classification loss and KD term. The larger weight favorably improves performance. Our proposed KD method based on these three analyses exhibits superior performance to the other KD methods. More experimental results including transfer learning are shown in the paper. Conclusion. Through analyzing KD process, based on disentangled formulation, we especially propose effective knowledge distillation, to refine the teacher probability. It is generally applicable to most of KD methods, instead of raw teacher probability, and it improves performance. Thank you for your attention.